Welcome, everybody.
Yes, go ahead, Frank.
All right, so today I'm talking about generalized descriptive set theory. And
Oh, do you want to go right ahead with the talk, or maybe we should say hello to
well,
everyone? And
actually, the first page of my slides, says that. So let me go to my slides.
oh, okay, all right. So you'll do that. So then let me make you co-host, though, because otherwise. Okay, so why don't you try and share your slides, Frank?
Okay.
All right, so our first speaker is Frank Tall, and his title was just there, but now it's gone. So you have to say it yourself, Frank. All right.
Okay, but
Go
I
ahead.
wanted to start off by just saying a word or two about the seminar. Founded in 1969, we meet at the Fields Institute, and for entirely too long, we've been meeting virtually. It's called the Set Theory Seminar, but members also work in whatever they're interested in, which is, for example, general topology, model theory, combinatorics, operator algebras, Banach spaces, non-standard analysis, or whatever. So the regular members from University of Toronto and from York University are up there. And then we have our current postdocs. And then there are graduate students, too numerous to name, and independent scholars and anybody else who shows up, which it's easy to do virtually. And David has shown how to subscribe to the mailing list. He'll show it again, I guess, at the end. But the normal meeting time is Fridays, 1:30 to 3. Today we'll run a bit longer. Okay, so descriptive set theory deals with definable, whatever that means, subsets of the real line in particular. And there's a history there of more than 100 years, things like Borel sets and later projective sets, whatever. And the idea is that these are nicely behaved, they're measurable, or at least consistently they're measurable. But if you throw out the definability, then you get, using the axiom choice, non-measurable sets and whatever. So people have tried to generalize this from the original context of the real line to other contexts. One that's popular now is quite set theoretic. It looks at analogs of descriptive set theory on kappa to the kappa rather than the irrationals, which is omega to the omega. This is fine and interesting set theoretically, but it's not clear what applications it has. There's another line of attack started by Froelich, Choquet, and Rogers and Jane in the 1960s and later. Also, there was Stone tried to generalize this to non-separable metric spaces rather than the usual Polish spaces, separable, completely metrizable. I don't think that worked out very well. Another line of attack that I just mentioned was reasonably successful in generalizing the analytic sets, that is the continuous images of Borel sets, to what are called the K-analytic sets, which are generalizations of analytic sets to spaces that are not necessarily separable metrizable. And curiously, nobody seems to have tried before me to generalize the K analytic sets, which have been used in functional analysis by a variety of people, to the K projective sets. So K analytic is to analytic, as K projective is to projective, and so forth. So that's what we're going to be talking about today. Borel sets are closed under complements and countable unions. Now, if you furthermore close under continuous real valued images, you get first the projective sets, and then if you continue that hierarchy, you get the sigma projective sets. So they're closed under complements, countable unions, countable intersections, continuous real valued images. And the notation, you have sigma 1, 0 equals pi, 1, 0 equals Borel, and sigma 1 alpha plus 1 equals the continuous real valued images of sets in pi 1 alpha. Just a minute, minor technical difficulty. Okay. All right, so you would have sigma 1 alpha plus 1 is the continuous real valued images of the from the previous place in the hierarchy, and then the pi's are all the complements of those. And then at limit ordinals, you take unions. Now, and so if you do that up to omega 1, you get the collection of sigma projective sets of reals. Maybe these haven't been looked at too much, because to do anything useful with them, you have to assume sigma projective determinacy, but that's okay these days because that just involves assuming some large cardinals. All right, the K analytic sets, generalizing the analytic sets, these are defined in two ways. One is the upper semi-continuous compact valued image of the irrationals. Iván in the next talk will explain what that's about. An equivalent definition is they're the continuous images of Lindelof check complete spaces. And check complete means absolute G delta, that is G delta in any compactification, in fact, any superspace. And that's a simultaneous generalization of complete metrizable and locally compact. So here you're no longer a subset of the reals. However, when you bring it down to the reals, K analytic subsets of the reals are in fact analytic, continuous images of Borel.
What does compact valued mean?
Yeah, that's we're going to leave for Iván. I'm just mentioning it here. For the purposes of my talk, we'll just consider the K analytic sets as the continuous images of Lindelof check complete spaces.
Oh, of course, yeah, that's.
All right, so in defining the K sigma projective spaces,
Wait, no, but I have a little question still.
Yeah.
Like, what target spaces do I mean,
Any target spaces.
any target space.
Yeah, so this is what's different from the usual analytic and projective hierarchy, where you are all looking at subspaces of some Polish space, such as the reals. Here, there's no such restriction. And this gets more complicated when you start trying to throw in complementation and continuous images. So rather than taking the complement, we're going to define the K sigma projective spaces by taking stone check remainder, or really could be any compact remainder in a compactification, and allowing arbitrary, not just real valued, continuous images. All right, so immediately you see some obvious problems because now you're dealing with whole classes of spaces. You don't have a class problem when you're dealing with the usual projective or sigma projective hierarchy. However, you can avoid dealing with classes by noticing that if you have if you have arbitrarily large inaccessible cardinals, then you can just look at the V kappas and notice that when you're working in a particular V kappa, strongly inaccessible, complementation, stone check remainder and continuous image do not take you out of V kappa. So you can think of this as just all these V kappas getting bigger and bigger, and then you don't have to deal with classes. This is arbitrarily large inaccessible cardinals is a relatively innocuous assumption these days. And in fact, we need to do more than that to get the amount of determinacy we need. All right, so is this useful? All right, so the K-analytic sets, as I said, have been used in functional analysis. Can I do anything with the K-sigma-projective spaces? And so I'm going to give an example in selection principles theory where I can do something with it. So the key concept here, a space is projectively sigma projective if all of its continuous real valued images are sigma projective. Similarly, and this was defined long before I started working on this, Arhangelski defined it projectively sigma compact if a space had all its continuous real valued images sigma compact. Okay, the main theorem here is that every K sigma projective space is projectively sigma projective. When you map it down to the real line, you get a sigma projective set. This is not so easy to prove, and Iván will show that in the next talk. And using that, we get a non-trivial theorem. All right, people who have come across selection principles before have probably heard about Menger and Hurewicz subsets of the reals and question of whether Menger implies Hurewicz or sigma compact or whatever. The definition of Menger is relatively simple. It's a generalization of Lindelof, or a special kind of Lindelof, I should say. If you have countably many open covers, you can get finitely many open sets from each cover, such that if you take the union of them, you get an open cover. So stronger form of Lindelof. Hurewicz has a complicated definition. I can never remember it, but if you take a look at it here, you can see it has some sort of the same flavor as Menger. Anyway, this is the classical definition. I guess you can figure out who it's due to. And I prefer, because it's easier to remember, at least for me, an equivalent definition that a space is Hurewicz if whenever you take a check complete space, including X, you can fit in a sigma compact space between X and the check complete space. All right, so it's not too hard to show that sigma compact implies Hurewicz, implies Menger. It's hard to show that the arrows don't reverse, but that is the case. And people working in selection principles have amassed a variety of results about when the arrows go back. And the general theme is that for definable sets, however you define definable, Menger definable sets are consistently, possibly assuming large cardinals or something, they're consistently sigma compact. On the other hand, Fremlin and Miller showed that phi equals L implies there's a pi1,1 or co-analytic Menger subset of the reals, which is not Hurewicz. But on the other hand, if you assume co-analytic determinacy, you get co-analytic Menger subsets of R are sigma compact. So lots of undecidability going on here. On the other hand, if you try to see what you can get without extra set theory, Arhangelski showed that analytic Menger sets are sigma compact, where you can define analytic even to be continuous images of Borel without requiring them to be real valued continuous images. Okay, I showed in my paper on productively Lindelof spaces that Lindelof projectively sigma compact spaces are Hurewicz using Arhangelski's methods. And as a corollary of that work, I was able to show that K-analytic Menger spaces are Hurewicz. But there are ZFC examples of K-analytic Menger spaces which are not sigma compact. So the situation we have is sigma compact implies Lindelof plus projectively sigma compact implies Hurewicz, implies Menger, and without extra restrictions, no arrows reverse. All right, so our theorem is that the axiom of sigma projective determinacy, which follows from large cardinals and talks about games being determined on sigma projective sets, this implies K sigma projective Menger spaces are Hurewicz. And so let's see how this is going to go. All right, well, we need the main theorem that K sigma projective spaces are projectively sigma projective, and that sigma projective determinacy implies sigma projective Menger subsets of the reals are sigma compact. And that's proved the same way as Fremlin Miller do the co-analytic, and other people, including myself, have done for projective. Okay, so continuous images of Menger are Menger. That's just like continuous images of Lindelof or Lindelof. And so sigma projective determinacy is going to imply that K sigma projective Menger spaces are projectively sigma compact. And then since they're Lindelof and projectively sigma compact, they'll be Hurewicz. And so that'll prove the theorem. Okay, so that's a quick introduction to the K sigma projective hierarchy and a possible application. I think there are probably some applications to functional analysis. I just have to find some graduate student to go through all the K-analytic uses in functional analysis and see which of them work for K sigma projective, assuming sigma PD. I suspect some of them will go through, some of them won't. We will see. But anyway, we've extended the spaces that you can plausibly call definable to a much larger class than previously. And so hopefully those will have some good applications. Thank you.
Thank you, Frank. Very interesting. So are there any questions from the audience? I have a question. Well, other people hopefully make up their mind to also ask something. But okay, maybe it's a stupid question. I don't know. This thing that it reminds me a little bit of universally bareness. It's sort of, maybe it's dual because you know, you're not restricting the domain of spaces, and with universally bareness, it's more sort of the other way around. But is there any relation between these notions at all, or is it just superficially similar?
Well, both are attempts to, I guess, make definable as wide a class as possible. But if I remember correctly, aren't universally bare spaces subsets of the reals?
Yeah, exactly. So in that sense, it's
Yeah. But what you
probably
could
not.
do to make the class I'm talking about even bigger is look at the K universally bare spaces. You know, just like
Oh, right.
I didn't have to use sigma-projective. It just seemed the easiest, most natural collection of definable subsets of the reals to use, but I could have used those subspaces of the reals which are in L of R, for example, and then use projectively L of R to get an even larger class of spaces. So yeah, why not projectively K universally bare spaces is a perfectly reasonable thing to think about. I don't know about universally bare, but I do know it is consistent that, let's see, that I believe it's equally consistent with an inaccessible that Menger subsets of the reals which are in L of R are sigma compact. So you are going to get some results for projectively in L of R.
Oh, I see. Uh-huh. Okay. So would I see?
So if I
Are
may do
there?
propaganda here, I mean, the stuff on Capita the Capo, which is quite popular these days, it's interesting set theoretically, but are there any applications anywhere else? I don't know. But here we at least have a chance of applications elsewhere.
Right. Are there any other questions? Huh, okay. So, well, then maybe we move on to the next speaker. Thank you again, Frank. And the next speaker is Iván Ongay Valverde, and I think it's kind of a continuation of this talk, isn't it? All right. Iván, um, would you share your screen?
Yeah, I will start sharing. So we will close Frank's. And here we are.
All right, so the next speaker is Iván Ongay Valverde, and his title is Upper Semi-Continuous Compact Valued Functions on the K-sigma-projective hierarchy. Go ahead.
Okay, yeah. So first of all, thank you very much. I'm happy that the seminar was invited to be part of the World Logic Day, and I hope everybody is enjoying. This is a continuation of the last talk. And as Frank announced, I will be talking about the upper semi-continuous compact value functions. And I will actually define the whole K-sigma-projective hierarchy. At the moment, I'm a postdoc, as Frank mentioned, in the University of Toronto, Mississauga. And yeah, thank you very much for being here. So yeah, so let's start. This is the plan for the talk. We will go little by little through it. So first, a disclaimer. We will be working exclusively with Hausdorff completely regular spaces. This is to make the stone-check compactification nice, because otherwise the space doesn't get included nicely. So this is an assumption that I will not mention again, but it's going to be in the background. Okay, So first, definitions. So we will talk about multifunctions, which are, it's a function that goes from x to y, but instead of selecting a point, you select a subset of y. Now, you can be thinking, okay, why don't we describe this as a function to the power set? And the reason is that mentally, it is really useful to think it as a function to the space, because then you can use again the topology of the space. We will see an example soon about that. Okay. Now, upper semi-continuous, like a multifunction is upper semi-continuous, and whenever the outer inverse, those are everything that intersects certain set of a closed set, is closed. And this is equivalent to say that the inner inverse of an open set is open. Now, notice that for single valued functions, like the usual functions, the outer inverse and the inner inverse are the same, and this is just continuity. Okay? So a little more definitions. So we say that a function is upper semi-continuous compact value, and I will be using the term USCCV because the other one is a mouthful. So whenever it is upper semi-continuous, and for each point, you assign a compact set. Now, this is the first example where I say that it's useful to think of the topology of the space Y, because we say that a multifunction is closed whenever the image as like the union of all the points in C of a closed set is closed. And this is just like translating the idea from closed functions. And we're using the topology on Y. And finally, we say that a multifunction is perfect USCCV whenever, of course, it is USCCV, it is a closed function, and the preimages of singletons, the preimages of points, are compact for everything. Once again, this is the same definition as with usual functions. A perfect function is the same, just that it's a function instead of a multifunction. Okay, so why talk about them? So as you can notice, points are compact. So asking for a multifunction to select compact subsets can be seen as a nice generalization. And this was also seen as a generalization of the inverse of a compact, of a perfect function. Wyborn in 1969 actually makes a whole argument about saying that this is the correct generalization of continuity. And in his paper, he argues, like, for example, saying that the inverse of a multifunction is a multifunction and other things like that, that is a better way to describe some results.
Can I think of this as a topology on the space of compact sets?
You could, but I will not be super sure how you translate that.
Okay.
Okay. I'm sure there's a way to do it, but it's usually just thought as the topology in Y. Okay. And for example, what the reason this is a generalization of inverse of perfect functions is the result of Wyborn, that a multifunction, even if it has no continuity property, if it's closed and has compact inverse values, then the outer inverse is USCCV. Okay. Also, the images of compact sets under USCCV functions are compact, which means that when you put them together, like composition of USCCV functions is actually USCCV. And finally, if you remember for metric spaces, like if you have a sequence that converges to a point, then the image of the sequence converges to the image of the point. And Wyvern show using filters, although he doesn't mention that word. It's a little like weird notation, but he's essentially saying that if you have a filter that converges to a point, then the accumulation points of the image of the filter are contained in the image of the point. And you can do examples that make that contention proper, but it's still the same idea that somehow you are getting closer to the image of the limit. Okay, and all of these were proved by Wyvern in that paper. Okay, and actually you can get more about these USCCB functions. The first part, and as Frank mentioned, we will be working a lot with the stone check compactification. It turns out that you also have this same theorem of extension, that if you have a function from any space to a compact set, then you can extend, not continuously, but USCCBing the function to the whole stone check thing. And furthermore, and this is also part of the classic theorem, if it is a perfect USCCB multifunction, then the image of the complement goes to the complement of the image of the usual set. Okay. Now, something interesting about this proof is that once you go through it, you actually don't use anything special about the stone check compactification. But once you think about it, what is special about the stone check compactification is that whenever you have a single value function, the extension is also single value. I am not pretty good with category theory, but I am not sure if this can be expressed as a universal property in the realm of, like compact spaces and USCCB functions, multifunctions. Okay. Now, another nice property is that the outer inverse of a perfect USCCB function is perfect USCCB, which, given the first result of Wyvern, should not be impressive because he had almost this without continuity. So you kind of get everything little by little. And finally, this lemma turns out to be more important than one will think, because USCCB multifunctions can be translated to usual functions. So what you do is you look at the graph space, which is just what you imagine. You put each point across the compact set you are taking as image, you union all of them, and it turns out that this space is the perfect pre-image of X, and then A is going to be a continuous image of this space. Okay, and this lemma was shown by Rogers and Jane in 1980 in a chapter of a book that is called K-analytic sets. And this is essentially how they prove that the equivalence of definitions for K-analytic sets that Frank mentioned, okay, which we will actually talk about them right now. So, as Frank, and the space is check complete if and only if it is G delta in some or any of, that is actually any of their compactifications. As Frank mentioned, it is generalizing being completely metrizable and being locally compact, right? On the other hand, okay, so then a definition, as Frank said, is that a space is K-analytic if and only if it is a continuous image of a Lindelof check complete space. And Rogers and James show that this is equivalent of being the USCCB image of the irrationals of omega to the omega. For one side of the proof, they use this lemma about the graph of the USCCB function. And because the graph is the perfect preimage, and omega to the omega is check complete, the perfect preimage is also going to be check complete. They don't prove it that way. They go to uglier definitions, but that would be like the simpler proof. Okay. So now we can continue defining everything. So we have defined K-analytic as Frank. Okay, so this definition for co-K-analytic of or K-pi11 is different from Frank, because what I'm saying is that the space is homeomorphic to a stone check reminder of a K-analytic. The way Frank defined it, he was saying that the stone check reminder of the space was K-analytic. But I will show in a second that is the same, right? So it is a pretty nice way to, I mean, the hierarchy behaves pretty well. And then you continue defining it as Frank did. Like the sigma parts are going to be continuous images of the pi parts, and the pi parts are going to be complements of the sigmas. Okay, and at limits, you just take units, countable units. Okay. So this is a quick reminder before our first proof. So remember that classically, given a perfect function from A to B, if you take the stone check compactification of A and any compactification of B, but let's say also the stone check one, and then the function restrict to the image is perfect, and to the complement is perfect, and it goes inside the complement, also the reminder. So reminders goes to reminders. And they are actually equal when the image is all of B. So the lemma is that given a K-pi11 space, the reminder is K-analytic. So how do we do this? By definition, there should be a space, a K-analytic space Y, such that the stone check reminder is X. It's homeomorphic, but let's say it's X. Then the closure of X in that space is a compactification of X. So using the above, the above fact, there is this function that is extending everything, where restrict to H to X is the identity, and the reminder goes to the reminder. But the class of these classes are pretty nice, and you can show that they are close on their. The first countably many are close on their countable and unions and intersections, and all the others at least are close on their finite ones. So you can take that intersection that is also going to be K-analytic, and this is the perfect preimage of. So the complement is a perfect preimage of that, and a perfect preimage is a USCCB function. So if this originally was a USCCB image of the irrationals, the reminder of X in its stone check compactification is also that, which means that the reminder is also K-analytic. Okay, and this strategy of taking the stone check compactification actually lets you prove a lot of things. You can show that all the sigma classes are close on their continuous function and actually on their USCCB function. You can show that all the classes are close on their perfect preimages. You can show that in any compactification, the reminder is going to be the other class, right? For a sigma, it's going to be a pi of the same level. For a pi, it's going to be a sigma. And you can also show that perfect images and perfect USCCB images of the pi ones are the corresponding pi ones, okay? And finally, for example, for projective spaces, we have that if there is a function from a Polish space to another, then the inverse of an analytic is analytic, the inverse of a co-analytic is co-analytic, and so on. And we get the same here. I put the result with compact spaces. It will also be true with check complete ones, and even maybe with k-analytic ones, but that is like going a little too much. Okay, and most of these proofs use, as I was saying, the stone check extension, and the first one uses the lemma about the graph of USCCB functions. And to finish the talk, I will show that whenever K1, whenever one of these K spaces is separable metrizable, is actually the same level of just projective, of usual projective one. So they are just like subsets of the reals. And this implies that the classes are projectively sigma-projective, which was really important for Frank's result. So we will sketch one, and then two just uses that the closure of these sigma classes under continuous images. So how do we do this? This is already published. So for K-analytic, Rogers and Jane already did it, so nothing to do there. Now for the pi ones, I will just do the base cases, and then everything is going to be clear how to continue. For the pi ones, if one is metrizable, you can look at two compactifications, a stone check one and a Polish one, okay? And using again this same property, universal property of the stone check compactification, you get that the complement is K-analytic. But using point one, if it's K-analytic, it's actually analytic, which means that the complement is co-analytic, okay? Which is just pi 1, 1. So we are going good. Everything is going well. So now the next step is going to be weird, but we're going to do a diagram chase to show that every separable metrizable K sigma 1, 2 space is a USCCB image of a co-analytic space, okay? So we get all the participants of the show with the properties that we want. And we start doing the same. We take a Polish compactification of Y, and we extend the function. And then we notice that f to the minus 1 is a perfect USCCB function from this Polish space to beta, to the stone check compactification of X. So by point 6 of the last theorem, like the one about pre-images, the pre-image of X is K pi 1, 1. And that pre-image may not be the same as f of X, because remember that is the outer inverse. So there can be like more stuff like around. So, and furthermore, so this pre-image is going to be co-K-analytic, separable metrizable, so it is co-analytic. And again, doing the diagram chase, you can notice that this, taking the inverse and then the function, the hat function, you take this coanalytic space, this coanalytic space to the image that is y. Okay. So we're almost done. We just need to show that y is actually an image of a coanalytic, not a USCCB image. Okay. Now, in this whole diagram chase, we need to be careful because in general, it is not true that these equalities happen. And at least this second one is always true for usual functions. Okay. But because the original f hat is a normal function, things work out well. Okay. So the final step, we're going to use the graph theorem. Okay. So if we have a separable metrizable K sigma 1, 2, it is going to be a USCCB image of a coanalytic space. Okay. So we take the function, that multifunction, and we know that the graph is going to be a perfect preimage of this pi11 thing. And furthermore, the graph is going to be inside x times y, that is metrizable times metrizable. So the image is a K pi11 space that is separable and metrizable. So it is pi11, which means that y is the single value continuous image of a coanalytic, which makes it sigma 1, 2. And as you can see, you can, from here, then you can repeat the process. You can say, okay, if you have a pi1, 2, the complement has to be K sigma 1, 2, and both of them are metrizable, separable, and so on and on. So the successor cases is just what we did, and the limits are easy because the projection of a union is the union of the projections. Okay, and that will be it. Thank you very much for your attention.
Thank you very much, Iván. Are there any questions for Iván? I have one. So it seems that you've shown much more than Jane and Rogers, but you also said at some point that I think you have a simpler proof of some of their theorems. Did I catch that right?
Yes. Yeah.
Is that...
I did mention that. Frank and I were talking about it yesterday. Jane and Rogers are analysts. So the way they proved that the graph of a USCCB function with domain omega to omega is check complete is using the definition of check complete of having these special like open sets that essentially there are some kinds of convergence, right? But it would be simpler to use stone check compactifications and take the perfect preimage.
Are you writing that up somewhere as well, or
yeah.
Is that... Oh, that's great. Okay.
I'm writing that. In the paper that Frank and I are doing, I do want to include that simpler proof.
Oh, cool. Nice.
And just as a comment, the way Rogers and Jane show that a K analytic separable metrizable is just analytic, they use some machinery that is, I think it's interesting on its own, but it's kind of complicated. And this same proof with the graph works. So it's also a simplification of that. Although I believe the other one can be used in other contexts. I'm not super sure which ones.
Okay, thank you. Are there any other questions? All right, then thank you again, Iván. And our next speaker, if I am not mistaken, is Clovis. Is that right?
I think so, yes.
Yeah, then
Here I
please
am.
go ahead and share your screen.
Yeah, the slides are right here. So you should be able to see the slides now. Is that true?
They're coming. No, they're not. Just see. Oh, now here they are. Okay, great.
Okay, very good. All right.
Yeah,
Hi,
go
everyone.
ahead. Yes.
Okay, thanks a lot. So today I'm going to be talking about the undecidability of the second order logic version of Morley's theorem on the number of countable models. This is joint work with Christopher Eagle, Sandra Mueller, and Franklin Toll. So
Mention that Clovis is a graduate student in the seminar.
very good. Under the supervision of Professor Toll. All right, so let's get started here. A little bit of motivation. First of all, Vought's conjecture from 1961, which remains one of the main biggest open problems in model theory, claims that the number of non-isomorphic countable models of a countable theory in first order logic is either Aleph zero or the continuum. And now Morley's theorem from 1970 is the best general result known so far, which says that the number of non-isomorphic countable models of a countable first order theory can only be Aleph zero, Aleph one, or 2 to the Aleph zero. For specific cases, Vought conjecture has already been verified, and this includes theories like the theories of trees, omega stable theories, O-minimal theories, and varieties in the sense of universal algebra, among others. Under CH, of course, Vought's conjecture becomes trivial. There is no other option for the number of countable models. So there are two alternatives. The first one is the trivial one, which is only consider Vought conjecture in models in which CH fails. And the other one, which is the one that we work with, is consider what we call the absolute version of Vought's conjecture and Morley's theorem, in which you substitute the continuum by having perfectly many non-isomorphic models. We're going to give the definition in the next slide, and this is the approach that we will follow. And we call it absolute because it's independent of the truth value of the continuum hypothesis. And perhaps originally we wanted to call it the topological Vought conjecture, but that may be mistaken already by people working in descriptive set theory. There is a version for Vought conjecture with concerns other equivalence relations, and so we resorted to the absolute name. So a very quick reminder on the descriptive set theory that we are going to be using. We are going to be talking about equivalence relations on the Polish space X, and remember that Polish means separable, completely metrizable. And then such an equivalence relationship is of a given Borel or projective complexity if it is of that complexity when regarded as a subset of X squared. And an equivalence relation E on a Polish space X has perfectly many equivalence classes. This is the definition that appeared in the previous slide. If there is a perfect subset of X such that all its elements are pairwise not equivalent under such a relation. So when there is no such perfect set, we say that the equivalence relation is thin. And on the other hand, it is something that's very usual in model theory, especially when one is interested in resorting to descriptive set theory to get some results, is that given a countable language L, it is customary to identify the space of L structures with 2 to the omega. The way that this is done is by considering 2 to the product of the arities of the relations in the language. We are going to use this identification freely throughout the talk. Now, let's talk a little bit about the isomorphism relation we are interested in. Counting non-isomorphic models, both in Bott conjecture and in Morley's theorem, and the second order version of it that we're going to see. The existence of a function which is an isomorphism is a sigma-1,1 statement. Remember that sigma-1,1 sets are continuous image of Borel sets. They are also called analytic. And this is not precisely what we are interested in. We are interested in the isomorphism relation among models of a given theory T, that is to say, in the set mod T, which is that of all the models of that theory, which is of course a subset of 2 to the omega under the identification in the previous slide. And therefore, the isomorphism relation in mod T, which is denoted like this, is defined as follows. So you declare that two structures are isomorphic with respect to T if and only if either neither of the two structures is a model of T or they are simply isomorphic. So the idea here is that we are sending everything that is not a model of T to one equivalence class. And so all we're doing is increasing the number of equivalence classes under this isomorphism relation restricted to T by 1. And on the other hand, well, this is definitely not a problem with the sort of computations of the number of countable models that we want to do, but there is a price to pay, and that is that the definition of this equivalence relation comes with that of the complement of mod T. That is to say, mod T appears, the complement of mod T appears on the definition of this equivalence relation. Therefore, the complexity of the equivalence relation that we are interested in is the minimum complexity that includes both sigma-1,1 and the complexity of the complement of mod T. So a little bit of what second order logic is about and the complexity of mod T is that, well, first of all, the main feature of second order logic is that it allows to quantify over subsets of the universe of the model. Many of us are familiar with this sort of things when we work again in descriptive set theory and we quantify over subsets of omega. There are a few subtleties here that are explained in detail and with examples in the paper. I have the link on one of the last slides. But for the purpose of this abridged version of the paper that I'm presenting here, the important part that we know is that, well, we're working with second order logic, and the whole deal is that we can quantify over subsets of the universe. So having said that, it's not hard to see that if you have a second order formula and X is a second order variable, then when you take a second order existential quantifier in front of the phi that you had, what you're doing in terms of the mod is taking continuous images. So that's how you come into the projective hierarchy. In first order logic, it's been known for decades, actually. That appears also in Morley's paper, that when you have first order sentences, the models of them are Borel. So by taking existential second order quantifiers, we start taking images, continuous images, that brings us to analytics. And then by taking negations, you start moving through the projective hierarchy. And eventually, if you consider theories where the sentences are unbounded in terms of their complexity, you get into the sigma-projective realm that Iván was mentioning and Frank were mentioning in the previous talks. So having said this, and the main idea is what I just said about second order existential quantification. When you have a countable language and you have a second order sentence, then the models of that sentence is a projective set. More specifically, when sigma is a for every n formula, that is to say a formula that has n quantifiers, n second order quantifiers starting with a universal one, then the models of sigma is that pi1n set, and if sigma is there is n formula, that is to say n second order quantifiers starting with an existential one, then mod sigma is a sigma 1n set. So again, the proof here is induction on the complexity of the formulas, and the only interesting case that's not the same as what happens in first order is the existential second order quantifier, and that's simply taking continuous images. Once again, that's why you came into the territory of projective sets. So we've been discussing equivalence relations and projective sets, and this brings us to this theorem of Burgess, which says that a sigma 1 thin equivalence relation on a Polish space X has at most Aleph1 equivalence classes. So more sophisticated, although the ideas were already there in the original paper by Morley, a more sophisticated proof of his theorem is simply an application of Burgess' theorem, and actually that gives you a little bit more, which is, well, Aleph less than or equal to Aleph1, or perfectly many. That's of course in the context of first order. But like with many things in descriptive set theory, when you go above analytic, then you start getting into independence result, and that's what we're going to be seeing in this case for the isomorphism relation restricted to a given second order theory. So the consistency of the failure of second order Morley's trichotomy goes as follows. It is consistent with ZFC that there exists a countable second order theory with exactly Aleph2 non-isomorphic countable models, while the continuum is Aleph3. So I have a sketch here, the idea of the proof, which is to work with the language of set theory and start from L, then force to add Aleph2 coherent reals over L, and then add Aleph3 random reals over the resulting model. We then write down a theory, which is a little bit complicated. There are some long formulas there, but they're in the paper. If you are interested in reading about it, it's already on archive. And that theory is such that the isomorphism classes contain a model of the form L delta R, where delta is strictly less than omega 1, and R is a coherent real over L delta. And the crucial point in this proof is that it is known that random reals don't add coherent reals, so blowing up the continuum to Aleph3 doesn't add new models of the form L of a coherent real or L delta of a coherent real, which are the ones that we are using to count each of the equivalence classes. Now, for the consistency of the second order Morley's trichotomy, I want to start with the Foreman-Magidor theorem, which says that if it is consistent that there is a supercompact cardinal, then it is consistent that CH fails and every equivalence relation on the power set of R that is in L of R has less than or equal to Aleph1 inequivalent elements or a perfect set of inequivalent elements. So our result follows from the ideas of Foreman-Magidor, and you start with a supercompact cardinal, and you carry out the standard forcing iteration for producing a model of PFA. Then if T is a second order theory in a countable language, then it either has at most Aleph1 isomorphism classes of countable models, or there is a perfect set of non-isomorphic models of T. The ideas here are that when you start with these sets that are definable from the real itself being smaller than a supercompact, then you can see that it appears at an initial stage of the iteration, and CH happens cofinally often, so you can assume that CH holds at that stage without loss of generality, and therefore you have at most Aleph1 isomorphism classes, and by absoluteness, if it was thin, it remains thin. So those are the ideas behind this one. And then what I was mentioning before is that in the paper, there are a few more things. The paper is much longer than what I can cover in a 20-minute talk. But there are applications to game quantifiers, to partially ordered quantifiers, to infinitary logics, and others. They're much sharper and very interesting large cardinal results. You also have further results on thin equivalence relations, more on the descriptive set theoretic side. And you also have several examples, both in model theory and in descriptive set theory. So thank you very much. That is it for now.
Thank you, Clovis, for the very nice talk. Are there any questions?
Yeah, hi Clovis. I do have a question. So,
Okay.
so I mean, in this example that you made with the coin reals and the random reals, how complex is like the theory completely?
Oh, yeah, it's a delta 1-2.
Delta 1-2.
Yeah.
Okay, so like the theory of each L delta R is a delta 1-2.
No, it's a theory that not the theory of them, the theory in which each equivalence class you have a model which is of that form is what's delta 1-2. The theory itself is rather complicated. It has some very long formulas, but we have a very careful computation of the complexity of it in the paper. I think it would be just another 20-minute talk to show the theory and compute the complexity and do the details, but yeah, it's a delta 1-2.
So just to like so like the theory is probably just like omega projective or something like that, but you're able to like bring it down to the complexity of the collection of all the models.
What I'm talking about is the complexity of the isomorphism relation. Remember, that's in the end what matters is this one that's in this slide. That one is delta 1-2.
Okay, yeah, thanks.
All right, you're welcome.
I also have a question.
Yes.
So does PFA imply the trichotomy, the proper forcing axiom? Because you said it holds in the standard model for the proper forcing axiom, but you didn't say that the proper forcing axiom implies it. I'm wondering.
Sorry, can you repeat, David? It cut out.
Yeah. So your theorem here says that, or your proof says that, in the standard model for the model that one usually builds for the proper forcing axiom, the trichotomy holds. But you didn't say that the proper forcing axiom implies Morley's trichotomy, second order Morley's trichotomy.
Okay. Interesting.
Maybe I can answer that.
Yes.
Yeah, we used the model of PFA because that was it was convenient to quote Foreman-Magador's theorem. You can get much stronger results by looking at it more carefully, and so you don't, in fact, need a super compact. You basically need just a bunch of wooden cardinals to get this, and PFA implies there are wooden cardinals. Am I right? And so that would
Yes.
question.
Right. No, it actually doesn't answer my question, although it's a very interesting answer, because I asked if PFA outright implies it. So that, I don't think this is really, I mean, so you're saying actually you could force it from much less.
Yes.
You could force it directly, but that still doesn't tell you that just assuming PFA will imply that this second order trichotomy would hold without going through forcing. Just, you know, apply the proper forcing axiom and work in the ground model. Probably, yeah, I don't know.
It probably does, but I'll have to think about that one.
Yeah, it's true. It's a very good question, but I don't think we have an answer, right? And whether PFA, as David is saying, straight up implies a trichotomy. That's an interesting question indeed.
Cool. I'm glad. All right. Okay. So thank you again. Unless there are any further questions, any other questions? Well, we should actually probably go on because we're running really late. So let's see. Thank you again. The next speaker is Spencer Unger, if I'm not mistaken.
Yeah, hi.
Cool. Hi, Spencer. Would you share your screen, please?
Yes, one moment. This one.
I can see it.
Okay, great. Let me make it big. All right, so I guess I'll start.
Great, thanks.
So this is going to be a real change of pace from the previous talks. I'm going to talk about flows in the torus. So let me explain. I guess I should also say, in order to do this in 20 minutes, I'm going to not mention quite a lot of history, and we're just going to go straight at the argument, which I think is understandable without a lot of background. So there's a famous question of Tarski, which asks whether a disk and a square with the same area in the plane are equidecomposable by isometries. So what that means is you take the disk, for example, and you partition it into finitely many pieces, and you move those by isometries, different isometries, to partition the square. Okay. And in the spirit of skipping quite a lot of history, this was solved positively by Laskovich in 1990. So it was open for a long time. And Laskovich used the axiom of choice in his answer. Just sort of a priori, there's no reason to believe that there's any kind of restriction on a measurable solution to Tarski's circle squaring problem. So this assumption that they have the same area is necessary, but it was still open whether you could do this in any kind of constructible way. So just briefly, let me say what the idea of the proof was. So you take a disk and a square, A and B, in the plane, and the first thing you're going to do is you're going to change setting to the torus. Okay, so if you take this disk and square and you translate and scale them down to live in a power of the unit interval inside the torus, then this equidecomposition result is going to hold in the torus if and only if it holds in the plane. Okay, so we're taking our whole big space R squared, and we're just going to focus down on this this little compact thing. So the action we're going to use is the action of translation on the torus. So this is the action of sort of addition modulo 1. Okay, so another feature of the result is that since we're working in this nice compact space, there's a probability measure, and we can choose things randomly. So select things from some fixed measure 1 set in the torus. And so these translations U1 through UD are going to give rise to an action of Z to the D on the torus. Okay, and then skipping oh so many details, this is the third point is how you find the equidecomposition. So you find an M, which is some bound, and you find a bijection between A and B, so that for every x, f of x has this form that I've written down here. So it's just a shift of x by n1 times the first vector u1, and then n2 times the second vector u2, etc. But the crucial point here is that you've actually only allowed yourself finitely many possibilities for how you're going to shift each x. Okay, so that's the point of bounding the sup norm of this vector n bar by your bound capital M.
So these are natural numbers.
Correct, right? Integers, if you like. Yeah, we should call them integers. That'll make it nicer.
Oh, right.
Okay, so using this bijection, what is the equidecomposition? The equidecomposition is the pieces correspond to these n bars. Okay, so there's a piece that we'll call a n bar, which is just the set of x where f acts like shifting using this n bar. Okay, and that's a partition of A. And then the isometries are exactly applying this appropriate vector of translations corresponding to n bar. Okay, so this is some kind of extremely rough outline of the proof. So the disk and the square are going to be equidecomposable by translations. We're going to find those translations by working in the torus and choosing some random ones. But then the translations we need are generated by the random ones, okay, under this action of z to the d. All right, so what I want to talk about is just one aspect of this circle squaring thing. Okay, before maybe a little bit more history. So in a 1992 paper, Laskovich gives a much more general sufficient condition for equidecomposability by translations. It turns out the important condition on A and B is that they have their boundaries, have upper Minkowski dimension less than K. And for the purpose of this talk, it's not going to be important what the definition of upper Minkowski dimension is. It's also sometimes called box dimension. It has something to do with covering the boundaries of A and B by boxes of smaller and smaller side length and watching what happens to the number of boxes that you need. Something like this. Okay, and the key to Laskovich's proof is some kind of quantitative refinement of the ergodic theorem for these actions of translations. And I'll say more specifically what these so-called discrepancy estimates are about. Okay, so we'll do that now, actually. How are we doing? Great. Okay, so in the end, I'm going to fix my translations U1 through UD, and I'm going to fix a starting point X in the torus. And here I'm going to define a set Sn of X. This is just all of the things that you can get to by shifting by, what I want to say, n1 times u1 and n2 times u2, etc. Okay, but under this bound on the sup norm. So this is just a finite subset of the torus. And here, I guess actually I want these n1 through nds to be natural numbers. That's a typo. Okay, so that, but that's not a big deal for the statement of this theorem. So the size of this set Sn of X should be capital N to the D. Okay, so what are these discrepancy estimates? Suppose that A is just a subset of a torus. It has positive Lebesgue measure, and it satisfies this condition that the upper Minkowski dimension of its boundary is less than K. Then if I take D large enough, so that just means I'm going to take enough randomly chosen translations. Then for almost every U1 through UD, I have this inequality down here. So let's just focus on the left-hand side of the inequality. What is this saying? I'm looking at this, this set Sn of X, which is like some kind of square. If you view the action of these translations as giving you a lattice inside the torus. then this Sn of x is like a square subset of that lattice with the base point at x. Okay, and so I'm asking how many points of A do I see inside this finite square? And the inequality is telling me roughly I see the Lebesgue measure of A times the number of points in the square. Okay, so this is an important point, and we'll pause here for a second to make sure that this makes sense. So there's some kind of action by translations. Inside this action, you have these very natural sets, which are squares. And this theorem is telling you that if you have one of these extremely nice sets where its boundary is not too crazy, then inside each one of these squares, literally every square that you draw like this, you see roughly the number of points that you expect based on the Lebesgue measure of A.
So, sorry, Spencer, maybe I'm reading something wrong, but
Yeah.
isn't m times n to the d minus 1 minus epsilon like a really big number?
Yes. Okay. So this is a good point. So this is the way I've written this. This is like a sort of unnormalized version. So the quantity that's going to be small or approach 0 is if you divide all of this through by capital N to the D.
Okay.
Okay, so in that case, what you're saying is the fraction of the points of A that you see inside the square is roughly the Lebesgue measure, and that estimate goes to 0 quite quickly.
Okay.
Yeah, that's a very good point. So whenever you write these discrepancy estimates, you have the choice of whether you normalize them by the number of points inside this square or not. So I agree that the normalized version is maybe a more intuitive thing to say here. Yeah, so right. So if you're looking in terms of like an absolute number of points, you just end up with some error, but the error is bounded in some nice way. Okay, but if you divide by this capital N to the D, then you actually get two quantities that are converging to each other.
Why isn't it just enough to say that it goes to 0 as n over minus 2?
Let me think. Probably because in general it's not true.
Oh, thank you. Oh, that's good. What
Right,
about n over minus 1? I mean, 1 over n.
Aha, yeah, okay, good. This is a very good point. So the crucial thing, I really should have written the normalized version, but if you normalize this, you get this n to the minus 1 minus epsilon. That n to the minus 1 minus epsilon is summable in n.
Ah, okay, that's what you want.
So
I
if you erase the epsilon, then you no longer get something that's summable, and that actually reduces the power of your theorem.
Right, thanks.
Yeah, so that's another extremely good point. Okay, the summability of this term on the right hand side, once you've divided, is a crucial piece of the argument. Okay, so this is the discrepancy theorem that we need. What am I going to say next? Okay, yeah. So Andrew and I gave this constructive solution to the circle squaring problem. And one of the key features of that I want to talk about is the notion of a flow. Okay, and the flow acts as a kind of continuous analog of an equity composition. So this was the reason that it was kind of a crucial in the proof, is that instead of just trying to construct an equity composition from scratch, we first constructed this continuous analog, and then we somehow fix the continuous analog to be a real one. Okay, so let me tell you just briefly what a flow is. So let's take a graph G that's on a vertex set V, and we're going to view the edge set as a symmetric and irreflexive relation. Okay, so it's really a directed graph, but the relation you get is symmetric. Okay, that's convenient for us. Okay, and then I'm going to define two collections. So xg is going to be the set of real valued functions on the vertices. And this capital phi g is going to be the set of real valued functions on the edges, with this additional property that the phi along some edge is negative phi along the reverse edge. Okay, and we'll see why we have this restriction in just a second. Both of these sets are groups under pointwise addition. It's just a kind of natural comment. So we're going to define an action of phi g on xg by this formula here. Okay, so maybe instead of reading the formula, I can try to tell you what the action is doing. So we're thinking of the function f as assigning a mass to every vertex. And then the function phi is going to tell us how to move mass around, okay? And the condition that if I move mass along an edge, phi of xy, mass along the edge xy, that should correspond to moving like negative mass in the other direction. That's why we have this kind of anti-symmetry condition, okay? And so this action of phi on f, this is exactly the function that you get after you move the mass of f according to phi. Okay, so the new value at x is just the old value f of x minus all of the contributions of moving the mass according to phi. Okay, so this is actually not how we phrased it in the original circle squaring paper, but this is a kind of nice way of thinking about what's going on in the background.
So you have some sort of mass distribution which is stable under starring with phi or what?
So I'll explain maybe in a slide or two how this is going to be related to this equidecomposition problem.
Okay.
So just the thing to think of is we have a function which represents sort of putting a mass at every vertex, and we have these possibly different flows phi that are moving the mass around in some way. And this action tells us how to move the mass according to phi. Okay, so this action has a number of kind of weird properties. So this is the first one. If you think about the definition of the action, you'll see that this is true. So the point in this definition of the flow action is that there's like a conservation of mass going on, right? The mass of f just gets redistributed by phi, right? So there's this weird phenomenon that acting by the sum of phi 1 and phi 2 is like acting by phi 2 and then acting by phi 1. Okay. Maybe even weirder is a relatively easy lemma that we won't prove, but I wanted to state for you, is that actually if I have some sums of both functions and flows that are both absolutely convergent, then I can interchange the limit and the sum, or sorry, the star and the sum in a way that you might not expect. So again, this formula from the lemma is reflecting a kind of conservation of mass, that happens because of this star action. But the moral of the story is that all of the kind of like distributivity laws that you might expect about this star action are not true. Okay, so we're going to kind of crucially use this lemma in a quick sketch of the argument. Okay, so to make a flow that's related to our equidecomposition problem, we're going to define a graph. Okay, and the graph is going to be kind of what you expect, right? We've been talking about taking an x and moving it by these translations. So I'm going to make a graph just by pairing up things that are sort of norm one away from each other. Okay, and then what did we prove? What was our continuous approximation to an equidecomposition? We took translations U1 through UD that satisfied the discrepancy estimates for both A and B. And then we found a bounded Borel phi, this function on edges. So that under this star action, it takes the difference of the characteristic functions of A and B to 0. So let's maybe David, this was the source of your question earlier. How is this going to be related to equidecompositions? It's this characteristic function of A minus characteristic function of B. So I'm thinking of myself as assigning mass 1 at points of A and mass -1 at points of B. And then the flow is trying to tell me how to sort of equalize those. Okay, and that's the condition of sending this difference to 0. Right, I'm sort of trying to cancel out the positive mass of A with the negative mass of B. So maybe a clearer way to restate the conclusion here is that actually we can think that when I apply this phi on just the characteristic function of A, it should turn it into the characteristic function of B. Okay, so yeah, I think that that's probably a better way, right? Because phi is telling you somehow how to redistribute the mass of some points, right? So I have this phi and I apply it to a function that gives mass 1 to every point in A, and then magically by this rearranging procedure, it produces the characteristic function of B.
Spencer, just to be super sure that equality is like actual equality, is not like up to
That's right. It's literal equality.
Okay.
That's right. So yeah, and the thing that's powering this is really those discrepancy estimates. I mean, you could imagine if you just picked an A and a B and picked some translations maybe badly, then the points of A and B wouldn't be nearby each other at all in the action. Right, maybe the A and B are so badly distributed inside the orbits of this action that you can't do anything. Okay, but the discrepancy estimates tell you that if you randomly choose enough translations, then actually there are going to be points of A and B close to each other. But not only that, you get this kind of bounded flow between A and B. Okay, so I am running out of time, but I think I can tell you just an outline of the proof of this theorem. So in the original paper, we had some complicated procedure for making this flow. And recently, over the past summer, we found a much simpler one, like extremely simple. So I'll tell you that in the next 2 slides, and then I'll be done. So we're going to write the final flow phi as a sum of these phi 2 to the n's. And we're going to show that this sum converges absolutely. Okay. Then we're going to define functions Fn, where F1 is the difference of characteristic functions. So that's like the starting state. The limit of the functions is going to go to 0 as n goes to infinity. And this crucial property is going to be that the nth phi, we're using phi 2 to the n in the sum, but whatever. So the nth phi, if I apply it on Fn, I get F2n. Okay, so these individual phi n's are like transitioning you through the sequence of f's. Okay, so why are these 2 bullet points enough? It's this extremely simple calculation using the lemma from a couple of slides ago. So I apply this phi, which is the infinite sum, on the difference of characteristic functions. There's this lemma that says that I can interchange the sum and the limit with the action of star. So that's what I did in the first line. And then there's this statement at just before the lemma that says, you know, acting by a sum of flows is like acting on them one by one. Right, so the characteristic function of A minus the characteristic function of B, that's F1. And when I apply phi 1 on that, I get F2. And then when I apply, oh dear, phi 2 on that, I should get F4, etc. Okay, and so the result of iteratively applying these phi 2 to the n's on the difference of the characteristic function of A and B is that I get F2m plus 1. Okay, and those functions go to 0 as m goes to infinity. And that's it. Okay, so it's enough to construct functions f and functions phi n like this. All right, and so what are those functions? I'm going to give you a definition of them on this slide, and then we'll stop. Sometimes things really turn out to be much simpler than you make them initially. So this is one of the morals of today. So to simplify this, we're going to define an action that we probably should have defined earlier. So n bar applied on x is just x plus this thing that we've been talking about all along. And that defines a free action of z to the d. And this Rn, I guess this is kind of a relative of Sn of x from before, but it's just the natural number version. So Rn is this square inside z to the d. So what's Fn of x? It's some kind of averaging function. So Fn at x, it returns you the average of the difference of characteristic functions between A and B over this square, which is like down and to the left of x inside the action. So that's the sum is over z in this minus Rn applied on x. All right, and then phi n is given by this slightly more complicated formula. But the formula here is motivated by needing to transition between Fn and F2n. Okay, and the proof that the Fn's go to 0 and that the sum of the phi n's is absolutely convergent, sum of the phi 2n's, whatever you want, is absolutely convergent. Those precisely use Laskovich's discrepancy estimates. Okay, and it's maybe not too hard to see that the discrepancy estimates should be useful here. So you're using the fact that both A and B satisfy the discrepancy estimates and have the same Lebesgue measure. So inside every square, they should have roughly the same number of points. Okay, so I guess maybe we've come all this way. I'll give you one last slide. So having simplified this this proof, a question that I had was, what can we say about the collection of phis that satisfy this sending this difference of characteristic functions to 0, right? We constructed this one by a relatively simple argument, but are there others? Is this the unique way to do this? Probably the answer should be no. And in some joint work with Anton Bernstein and Anush Saranyan, we showed that there are actually lots of these flows. And we showed that you can make ones with kind of specific combinatorial properties if you like. And in order to do that, you need modified discrepancy estimates that are sort of analogous to the ones that Laskovich proved. Okay, so I'm significantly over time, but I'll stop here.
Thank you, Spencer. Actually, I think you're doing great because you started really late and you caught us up a little bit. So I hope you didn't hurry too much.
No, this was great. That's exactly what I hoped to say.
Fascinating talk. Are there any questions?
Yeah, I have a question and a half, let's say. The first one is like, so you have been saying about like taking these translations randomly.
Sure.
So what is exactly what you are trying to avoid? Like, so like that measure one set, what are you taking away, right? Like,
let's see. It's a little bit complicated. So, let me think about what I can say in just a sentence or two. So, these squares inside the action, there's a natural uniform measure on those squares, which is just a normalized counting measure, right? Which is really in this discrepancy estimate, that term on the left-hand side where we're counting the number of points of A, that's like a normalized counting measure of A inside that for that square, right? So the discrepancy is really measuring like discrepancy between Lebesgue measure and that normalized counting measure for A. Okay, so what are we bounding when we randomly choose the translations? What we're bounding actually is the Fourier coefficients of that measure, of that uniform measure. So it turns out that the Fourier coefficients of that measure are actually independent of which square that you take. And the randomly choosing the translations will improve your bounds on those Fourier coefficients, which is what you need to prove this discrepancy estimate.
okay. So like you're taking away these like Fourier dependency somehow at each step, let's say. Like,
yeah, that's right.
Yeah, that's pretty interesting. Yeah, thanks. Yeah, and I just realized that my half question was not a question. So yeah, okay. I'm done.
Great. I actually have more questions, but in the interest of time, I will ask them. I don't know when I get a chance. Thank you again, and that brings us to our last speaker, and that's me. So let me get my slides ready. All right, does this seem to be working?
Yes.
Cool, okay. Oh shit, so that happened. Can you see the slides move as well?
Yes.
Okay, good. Okay, great. All right, so my title is Infinitesimals and Probabilities, and I'm also a postdoc at U of T, and I work with William Weiss, and Hasway Duanmu is a former postdoc, I guess, here, who just left and is now a professor in China. All right, so I have an outline here. I will first tell you about non-standard analysis at very high speed, and then I will tell you something about a thing called lobe measure spaces. So this is non-standard measure theory, also at rather high speed, and then maybe I will be able to actually prove something, and that's an answer to a question of Kiesler and Son concerning lobe measure spaces. All right, so non-standard analysis. In non-standard analysis, you extend the field of real numbers to a larger field, the field of non-standard reals, also called hyperreals, and they've got this star on the left, the star R. And as you might know, in star R, there are both infinite numbers, so numbers S that are bigger for every standard real R, bigger than R for any standard real R, and there are also infinitesimal numbers, so positive numbers S that are smaller than every positive standard real. So they sit, these non-standard real numbers, they sit very, very densely in the standard real numbers, and they also go off to the side. And here's some notation that you hopefully know. You say R is approximately equal to S to mean that they're infinitesimally close to each other. And you call a hyperreal near standard if it's infinitesimally close to a standard real. So it's not really far off to the side and infinite. It's also sometimes called a finite hyperreal. And for every near standard real, one that's infinitesimally close to a standard real, you denote that standard real by circ R, upper circ R. So that's a standard real that you're infinitesimally close to. It's also called the standard part. And the circ map is called the standard part map. All right, so I mean, so far this is just really notation. What makes it interesting to look at this field extension is that it comes from a saturated elementary embedding. So that's a map that assigns to it really more or less any mathematical object X its extension called star of X. So you always write the star to the upper left. And the crucial thing is that this is a structure preserving mapping. It's not just a field homomorphism, it's structure preserving in the strongest possible sense that you can imagine. It preserves truth of all statements of first order logic with bounded quantifiers in some sense. So, I mean, I'll just have to gloss over a lot of details here because it's a 20 minutes talk, but I hope you can get some idea out of it. So the star map has as its domain what's called a superstructure. That's a little universe built over the real numbers, call it V of R. So it goes from V of R into star V of star R, which is just the target model for this map. And you know, the superstructure is just built by first taking all the reals, then you take all the sets of reals, then you take sets of reals, and so on. You go for countably many steps, you get the superstructure. And to anything in this structure, you can apply the star map, and you will preserve all of the properties this thing has. So the reason we're doing this is because if we're doing probability theory, we want to apply the star not just to reals, but also to sets of reals. And I guess I could have stopped at V1 of R, but you know, I just couldn't help myself. Okay, so a set is called internal if it's an element of one of the levels after you've hit it with a star. So it's an element of the target model. And it's external if it's just a subset of the target model. So the funny thing about this, about non-standard analysis, is that the target model on the right side, the star of the superstructure, it doesn't really know about all of the subsets it has. It has internal subsets, which it can talk about, and there's also external subsets that it can't talk about. All right, so here's something to calm you down if you thought this was confusing. A picture of the hyperreals. They're really not that complicated. In the middle here, you've got the standard real number line, and then off to the side, you've got infinite hyperreals. And if you zoom in really close to a point, like the point 0, you see all the reals, all the hyperreals which have standard part 0. So everything that's infinitesimally close to 0, that's called the monad. And every point has a monad, right? 10 to the 6 also has stuff that's infinitesimally close to it. And of course, if you take 1 over an infinitesimal, then you land in the infinite. All right, so those are the hyperreals. Okay, now what are lobe measures? We're off to non-standard probability theory. So suppose that F is an internal Boolean algebra on some internal set omega. So now we're in the non-standard part of the universe in this V star, and you've got some internal star finitely additive probability measure. So you could just say finitely additive here if you want. That's maybe easier to think about. So the probability measure has values in the star of 0, 1, so it can take hyperreal values. And then you can consider an external finitely additive probability measure with domain F by just taking the standard part of the measure of each set. So now you have a finitely additive probability measure defined on this internal algebra of sets. And you could ask, can you extend it to an external measure, to an actual measure, a sigma additive measure on the subsets of omega? And the answer is yes. And although I can't give you too many examples in this short talk, it's incredibly useful to do so, because actually a lot of measures that you encounter in your life are of this form. They're extensions of such an internal measure, and that's sometimes very useful. Oopsie. All right, so can you extend, what is going on with my slides? I'm sorry. Right, so I said, can this circ measure be extended to an external measure on subsets of omega? And the answer is yes. And this is how you do it. So you look at the set of so-called lobe measurable sets, it's L mu of F. It's the set of all external subsets of omega which satisfy this condition here. So it's basically you're using a Kara-Theodori extension theorem. Oh, and the approximate sign in the middle should be an equal sign. That's a typo. So you take the Kara-Theodori extension of this circular measure to the largest possible set, or at least the set that's given to you by this Kara-Theodori extension procedure. So that's basically you're looking at the inner measure and the outer measure, and you call a set lobe measurable if its inner measure and its outer measure agree. And the funny thing is that this set L mu of F turns out to be a sigma algebra. So that's really nice. And this is by a property of the elementary extension called saturatedness. And this is the only time we're going to use saturatedness, or we need it, so I will not talk about it at all. But it's just, by a property of this elementary extension, this turns out to be a sigma algebra. Its members are called the lobe measurable sets. And now you can extend the measure uniquely to a complete measure, which is called the lobe measure, mu L, on this set of lobe measurable sets, by, of course, taking the measure equal to this supremum up there, where the sup of the circ inner measure if you want, or you could also take it to be the inf of the circ outer measure. It's the same thing. This is called the lobe measure. So this makes, so you get a standard probability space now, and this is called a lobe space. So the underlying set is still your set omega that you started out with, the internal set, but the measurable sets are now a sigma algebra of external subsets of omega, and you've got an actual sigma additive probability space here. And the funny thing is, and this is why people are interested in this, that a lot of spaces, a lot of measures arise in this way. For example, the Lebesgue measure you can think of as arising in this way, and many other measures, like the Wiener process can be constructed in this. Random walks can be constructed in this manner. So this is very useful. The useful thing is, I should say that the F can taken to be hyperfinite most of the time, and that's what makes it really useful. So here is the question of Kiesler and Son that we answered in our paper and that I want to talk about. So they said, suppose you've got two internal finitely additive probability spaces, M and N, they're both on the same set, omega. They're both on the same set, omega, but they've got different algebras, F and G, and different measures, mu and nu. But we suppose that they're lobe equivalent. So if you take the lobe spaces that generated by these, you get the same probability measure space. So Kiesler and Son then ask, so if you've got these two lobe equivalent internal probability spaces, do they have to be close to each other in some sense? So one way to say that they're close to each other is you can consider the algebra internally generated by F union G. Let's call this H. So that's all the internal finite unions of elements of F and G and complements of finite unions and so on. That's possibly a pretty large object, and that's actually the only place I need to use the star map on anything that's not a real. So you look at this internally generated H, and you can ask, how far is H from G and F? Well, I guess it's basically the same as asking how far is G from F. In particular, is there a lobe equivalent internal probability space whose algebra of sets is H? Which would mean that they're not very far away, right? Because that means that H, the lobe space that you get from H is again the same space as you would get from either M or N. Okay, and we answered this positively in the case where F is hyperfinite, and most of the spaces that you're interested in are where F is hyperfinite. So what does that actually mean, hyperfinite? Maybe I should say that, spell that out in more detail. An internal probability space is called hyperfinite. If F is hyperfinite, there's a P missing there, sorry. And that means that in star V of star R, in this target model, the cardinality of F is some non-standard natural number. So some n in the star of n. That means that, you know, the target model thinks it's a finite set. It's not actually going to be finite. It's actually going to be very large in most cases. But since the target model thinks it's a finite set, you can work with it as if it were a finite set, which is a very powerful tool. Okay, so here's the theorem that we proved. Well, okay, I should say again. So the reason that you're looking at these hyperfinite Fs is that the lobe spaces that you get from such hyperfinite probability spaces are a very rich class of measure spaces, and you find a lot of measures that you work with in practice among these, or, you know, they're sometimes your measure is just isomorphic to a lobe measure modulo a measure preserving function, namely most of the standard map function actually. All right, so this is why this is interesting. So the theorem that we proved is the following. Suppose that M and N are hyperfinite probability spaces which are lobe equivalent. That is, if you take their associated lobe measure spaces, you get the same measure space. Then indeed there is an internal finitely additive measure defined on H such that the lobe measure space generated from this new measure C is again the same space. All right, and well, I was going to show you some of the proof, but I think maybe that's not a very good idea because I'm way over time. So for some reason I thought I could show you some of the proof, but actually I don't think I will. So I just showed you the theorem and I hope you find it interesting. And I say thank you. That's it.
Yes, any questions? Okay, I do have a question. So if I understand right, what the theorem is proving is that whenever, even if you have like an external lobe space and whatever, you can bring it back to be an internal one, right?
Yeah, I mean, that's not our theorem. That's something that Loeb showed, and many people extended it. His result, yes, but that's true. Yes, you can start with an internal measure. You do this Loeb construction, and sometimes you also perhaps move to a space that's very similar to the Loeb space using the non-standard map, and you get a very useful measure, something like Lebesgue measure or a stochastic process. And so this is a method of viewing Lebesgue measure or stochastic processes and things like that as arising modulo this Loeb construction from a finite measure space. So, for example, Lebesgue measure arises from the uniform measure, where you decompose the real line into infinitesimal intervals, and each interval gets infinitesimal measure. But it's only hyperfinitely many infinitesimal intervals, and then you can calculate with Lebesgue measure as if it were just a finite sum, which in some contexts is very useful.
Oh, okay, I see. Yeah, thanks. Any more questions? No. So David, you were the host the whole time, so you should close the session.
Yes, so let me close the session by again encouraging you to subscribe to our mailing list. So you do that by sending me an email. I maintain a mailing list where we just announce our seminar every week, or we don't currently have it every week actually, but we announce it when we have one. And thank you everyone for joining us. This was a part of this World Logic Day declared by UNESCO, and that's why we had such a marathon of talks. I hope you enjoyed it. All right, I will now stop the recording.